Alright guys, I hope you're all doing well, and I hope the semester is going very well with you. So today I'll be talking about chapter 17, which is longitudinal waves. So you will see as we go along that longitudinal waves is very similar in many respects to transverse waves. Like if you manage to understand chapter 16, then this chapter should be a piece of cake. So in this chapter, we'll be solely discussing sound waves. So sound waves is an example of longitudinal waves, and if you have a sound source, say at point S, then sound waves, unlike transverse waves, they will be spreading out or transmitted in a spherical sort of manner. Like imagine you have a ball, and this is the center, the center be S, and then sound waves will be going in all 3D dimensions and will be spreading out in this way. So transverse waves, the one we took last chapter, like they spread in one direction, in a 2D direction, like a Y and X direction, in a Y and X coordinate system. But sound waves are different. They spread in a spherical manner. So this is the first thing you need to know. Another thing is that, so sound waves are something like this. So this is a sound wave, and we see here in this area we have more air molecules, and we have less air molecules in here. So we call the dense area, we call it compression. So the ones with too many air molecules is compression, and the one with little molecules called refraction. Alright, so the particles in sound waves travel like this, along the x-axis. So these particles in here will be undergoing simple harmonic motion in this direction, and in this axis. And the whole wave will be traveling in the same axis. So both the particles and the wave are traveling in the same axis, unlike transverse wave. So we can see that from the name, like longitudinal, you can see it as along the same axis, the x-axis. So the distance between a compression and another compression is 1 lambda, and the same here, a distance from two refractions is 1 lambda as well. Okay, so as we've said earlier, if we pick a point and then we pick another point in the wave in which the wave exactly repeats itself, then this is 1 lambda. So as far as the velocity of sound waves go, so we're going to have this equation. The velocity of sound waves is equal to the square root of bulk modulus over the density of the material. Okay, so bulk modulus, we studied it in Physics 101. It's equal to the pressure over the strain. So what does this mean? Like, how can we conceptually understand what bulk modulus is? Like, imagine that we have a very high pressure. Like, imagine that we have 10 to the 10 pressure, and we have a very small strain. Like, imagine we have 1, or actually 1.5. Then the value of the bulk modulus is going to be very high. So it means that if you apply a lot of pressure on something, and strain is basically the damage you can do to an object. So if you have very high pressure and very low damage, then the bulk modulus is going to be high. So the higher the bulk modulus is, the more resistant the material to strain or to deformation. So, and if it's the other way around, like if you have like a very high strain and very low pressure, then it means that we're applying very little pressure and the object is being deformed very highly, and which means the bulk modulus is going to be very low. So that aside, we can understand that this equation is equal to the how strong the material is, represented by the bulk modulus, over the density of the material. Okay, so density is equal to mass over volume, and it's a fixed value. Like as you increase mass, volume must be increased as well. Okay, so this gives you the velocity of the wave travel. Like it doesn't give you the particles' velocity. So we said that particles are undergoing simple harmonic motion around the center in here. Say this is the center. Then all particles on the wave are going some sort of motion like this. So this velocity here does not give you this motion, or the velocity of these particles. It gives you how fast the wave is traveling through a medium. Okay, so the velocity of sound waves in air is a well-known number, and it's 343 meters per second. And you should be memorizing this because in some problems they don't give you this number and they expect you to know it already. So this is the velocity of sound when the medium is air. 343 meters per second. Very important number. Alright, so in order to describe the motion of particles in longitudinal waves, we use a cosine equation. So this is very similar to the equations we learned in chapter 16, except here we have an SM. So SM is the maximum displacement. So imagine we have a line, this is the mean position, and we have a particle, okay? So the particle in a longitudinal wave will be going in this direction, displacing like this. So the cosine function starts here, and this here is the maximum displacement. So this distance is the maximum displacement for the mean value, which is represented by Sm. This distance is this distance, and it's equal to Sm. So as the particle moves to the mean position, the cosine decreases until it becomes 0. Then the particle moves in the negative direction. So it moves like this until it reaches here. This is the maximum negative displacement. So and the particle will be moving like that, like oscillating back and forth, and the wave will be going in this direction. So the particles are oscillating like this, and wave is going traveling in this direction. Okay, so omega here is the angular frequency, and k is the wave vector, or it's the constant, and it's equal to 2 pi over lambda, as we already learned in chapter 16. And x is the position of the particle along the x-axis, and t is the time. Okay, and this here is the output of our equation, and it gives you the position around the mean axis. Okay, so this here, if you understand this equation, you understand how we describe the displacement of the particles in a longitudinal wave. So a very related concept to displacement in longitudinal wave, we have a concept that is pressure, okay? So, and pressure will be decreasing as the particle displaces further. Imagine that we have a line here, and okay, and there is another particle oscillating, and this is the mean position of the other particle. So as this particle displaces to this direction, and this particle displaces to this direction, so the distance between the two particles will be higher, and the pressure is going to be lower. So pressure and displacement are inversely related. If we have a very high pressure, then we have a very small displacement. As the displacement increases, pressure decreases. So if you want to describe pressure, what function should we use? Well, a sine function would be suitable, because sine is completely out of phase with cosine, So sine omega, actually kx, okay, let me write this here, minus omega t is equal to change in pressure. Okay, so this here is the maximum change in pressure. So this means that, so we know how a sine function is, it's like that. So at this point we have zero pressure, it means we have maximum displacement. So the particles are very far away from each other. Okay, so, and at the top here, we have, this is the pressure amplitude. So this is the maximum value for which the pressure can change. The pressure cannot change in a value that is higher than this value. So this equation, it does not give you pressure, it gives you change in pressure, or the amount that pressure can change in a longitudinal wave. And you have to understand that at maximum displacement, we have zero pressure. And at minimum displacement, we have maximum pressure. And you need to understand as well that these two values, the displacement and pressure, are inversely related. All right, so a very important concept in longitudinal waves is interference. And this concept is very heavily tested in all exams and in all of the questions that I have seen. Like, I've seen so many interference questions that I think it's the most important section of this chapter. Okay, so if we have a source of sound waves here, and we have another source here, and we have a detector here, say we have an ear, a human ear. And so the waves will be traveling in a spherical manner. Okay, so this wave and this wave will be traveling in a spherical manner. And say the distance between the first source and the second source is equal to L1. And the distance between, so it doesn't have to be like slanted like this, it should be straight. The minimum distance, like we could go all the way from here like this. We don't care about this distance, so it should be a straight line. Let's call it L2. So if L1 minus L2 is equal to 0, which in this case is 0 actually, if this distance right here is exactly equal to this distance, if this is equal to 0, the distance, the difference in paths, or the difference between the distance traveled, then we have a completely constructive interference. And so if change in distance is equal to 0 or any multiple of lambda, like if it's lambda, then we have also constructive interference. So we could multiply this by n. So we're going to have lambda, or 2 lambda, 3 lambda, 4 lambda, etc. 0 and any multiple of lambda, it's going to be giving you constructive interference. Okay. So now imagine that the detector is actually here. This is the detector, this is another human ear. So the distance here between the first, or source 2, and the distance between source 1 and the detector are not going to be 0 or any multiple of lambda. Actually, this distance from S1 is higher than this distance. So we're going to have some value here. And if you have a value like half of lambda, if the change in distance is equal to half of lambda, then we're going to have a completely destructive interference. And if you add 1 lambda to this value, you're going to have 1.5 lambda, in which you're going to also have completely destructive interference. So if you keep adding lambdas, like 2.5 lambdas, and if you keep adding lambdas, then you're going to have completely destructive interference as well. So I hope these two things are clear, because these are very important to solve problems. And there is a very important note here, like if the distance between S1 and X is equal to the distance between S2 and X, when you have, for example, you have the whole distance as D from S1 and S2, and this is from here to here is D over 2, and here is also D over 2. Then if you have a point on this line, the X axis, any point actually, then the distance here between between S1 and this point, and S2 and this point, are going to be equal. And this can be seen with trigonometry. I'm not gonna go into the proof because you don't actually need it, but you have to understand that if you have this setup, then any point in this line are gonna be having the same distance from S and this one, S2 and S1. And as we move like away from this point, the distance from S1 starts to increase, and if we move up, the distance from S2 will increase, and so on and so forth. So one thing that I need to note is that when we have completely constructive interference, when we have interference at this point, then we're gonna have the highest intensity. So later we're gonna learn something called intensity, and so it will be highest, and the wave, the resulting sound wave will be having the highest amplitude. So we'll be having the highest intensity, highest amplitude, and highest power. Okay. So the power, or the amount of energy that is going to be transmitted through the wave, is going to be highest when you have completely constructive interference. And it's exactly the opposite in the case of completely destructive interference. Okay, so a very important concept in longitudinal waves is the intensity. So intensity is defined as the power over the surface area of the ball. Like, so we know when we have a sound wave traveling, it will be traveling in a spherical manner, as we have mentioned, and we know the area of a sphere is 4 pi r squared. So it's the ratio between, intensity is the ratio between power and this sphere area, surface area. Okay, so we could look at intensity as the rate of change, or the rate of energy transmitted per unit area. So it's a very similar concept to power in transverse waves, except we divide the power by the area of the sphere. And this value right here is also equal to 1/2 of the density of the material times the wave speed times the square of the angular frequency, and this is the maximum displacement squared. So intensity is equal to this, and is also equal to this. R here is the radius of the ball, so the distance between the source and the detector. So if a question asks you to find the intensity between this source and say an object at R distance from the source, so this here would be the detector. So we could look at the distance between the source and the detector as being R, and you could plug R here as the radius of the ball, and you could calculate the intensity. Alright, so sound level is basically another way to express intensity. So intensity and sound level are equivalent in a way. So they have the same unit, like the unit for sound level is watt per meter squared, and the unit for intensity is the same, it's watt per meter squared. So sound level is basically a logarithmic way to express intensity. And we have invented this way in order to make it easier to understand intensity, for us to understand intensity. So we have something called reference intensity. Reference intensity is very near to the lower limit of a human hearing range. So any range that is lower than this, we possibly cannot hear. Okay, so if you want to express intensity in sound level, you're gonna say that the sound level is equal to 10 times log of 10, and the argument of log of 10 is going to be our intensity, which we already defined as power per surface area of a sphere. So this here is this, divided by the reference intensity. And there is a very important note here. So sound level 1, sound level 2 cannot be added linearly, so to speak. Like, this is a false operation. If you want to add sound level, if an example tells you that we have sound level of 2 and we have sound level of 4, and the questions asks you to add them, then you have to convert the sound level into intensity through this equation, the whole equation. So to convert this to intensity 1 and this to intensity 2, and you can add them. So these values are linear, so they can be added linearly, but these values are not linear. They're logarithmic, some sort of exponential value. Yeah, so that's about intensity. So a lot of confusion can occur, but they're basically the same thing expressed in different ways. So similar to transverse waves, we have a concept called standing waves and longitudinal waves. And standing waves occur when we have tubes. Like, imagine this is a tube or a pipe or something of that sort. And imagine that this pipe is open at both ends. If we have a sound source here, and so sound will be traveling in a spherical sort of manner, it will be reflected like from these sides. Like, it's not like we need to have some sort of partition here in order for the sound waves to reflect. Remember, sound waves don't travel in a linear way, they rather travel in a spherical way. So if you have a pipe that is open at both ends, then the frequency for resonance, or the frequency for a standing wave to occur, is going to be the velocity over the wavelength, which is equal to n times the velocity of the wave, and if the medium is air here, then it's going to be 343 meters per second, and divided by 2L. So a very important thing to understand is that at an open end, we need to have an antinode. We cannot have a node at an open end. Like, here is a place where the wave does not move up and down, but so a node cannot occur at the end if the end is open. So our first harmonic is going to be something like this. Okay, so keep in mind that one harmonic in an open end, or a pipe that is open at both ends, is going to be half of lambda. So half of lambda is one harmonic. Okay, if you wanna combine these two, they're gonna look something like this. And this is half of a wave, or half of a wave, a lambda. So on this, then we have a 2L in the denominator. And n can range from 1 until infinity, but given that you increase in an integer form, like 1, 2, 3, 4, 5, etc. So if you're wondering, like, the second harmonic is going to be something like this. Yeah. So at both ends, we need not to have a node. We cannot have nodes at both open ends. And so this here is one half of a wave. And these two, if you combine them, this part and this part, you're going to have another half. So each half of a wave represents a harmonic. So our harmonic number here is 2. And you can increase it accordingly, like 3 and 4, etc. Here we have a pipe that is open at one end and closed at the other. So if you have a closed end, then we necessarily need to have a node here, a place where the wave does not move. And if we have an open end, then we need to have an antinode. So our first harmonic is going to look something like this. And keep in mind that this first harmonic is equal to lambda over 4, or 1/4 of a wave. Because if you want to complete this like picture, or to complete this wave actually, what we have here is something only in this part. Then this is a fourth. If you want to complete it, you're going to go like this. This is the other fourth. This is the third fourth, and this is the fourth. So in a pipe that is closed at one end, a harmonic, or when n is equal to 1, then we're going to have this part only. And if we're going to go to the next harmonic, we cannot add only 1/4 of the wave, because that is going to be something like this. And that's going to make the other end, the other open end, to have a node. So, and we already said that at an open end, like, we cannot have a node. So we need to add one more harmonic. So instead of saying that n is equal to 2, we say n equals to 3. So and if n is equal to 3, we can manage to have an antinode at this end. Okay, so our wave is going to look something like this. So this is one harmonic, 1/4 of the wave. And here another harmonic. And here is the third harmonic. So as we already said, that 1/4 of a wave represents a harmonic. So if we're talking about the third harmonic, then we're going to have 3/4 of a wave. 1, 2, 3. And we managed to have an open end here and an anode here. An antinode here and a node here. And this equation right here, since we have a harmonic represented by 1/4 of the wave, then we have a 4 here in the denominator. And this here is the number of harmonic, or the harmonic number. So if you know the harmonic number, and if you know the velocity of sound in the medium, say it's air, it's going to be 343 meters per second, then you're going to be able to figure out the length of the pipe. Like in questions, they could give you the length and the harmonic, and they want you to figure out the speed of the wave in a medium. It's not always going to be air, so this is well known, but in other mediums other than air, sounds travel in different speeds. The more compact the medium is, the faster is the speed of sound. For example, it travels through water faster than through air, because water molecules are more closely attached to each other. And that's about it. All right, so a very important concept in this chapter is called the Doppler effect. And what does this say? Like, what does this effect say? So if we have a moving source of sound, like imagine that this is a source of sound, and the source is emitting sound waves in this frequency. Imagine that it has a velocity to the right. So if it moves to the right, then the sound waves are going to be traveling like this. So the distance between, so this is going to look something like this. This distance right here is larger than the distance right here, which means that the frequency on the left side is going to be less than the frequency on the right side, or the direction of travel. So this distance is lambda, basically. So as the lambda decreases, frequency increases. So the idea behind Doppler effect is something like this. So if you want to go into the math of the Doppler effect, it says that if you have a traveling detector and a traveling source, so D for detector and S for source, Then we're going to have a new frequency. This is the actual frequency that the source emits. Given that it's constant, we're going to have this frequency. But if the source moves, like if the source or the detector moves, like this goes for both the source and the detector, then we're going to have a new frequency, or f prime, caused by the effect that we have showed here. So in order to understand how to use this equation, we need to understand the direction of movement. If the detector is moving close to the source, or is moving towards the source, then Doppler effect says that the new frequency should be higher than the original frequency. So if the detector is getting close or moving towards the source, then we want to make this value, or the numerator, to be as large as possible. In order to make this new frequency large, as we have already said that if it's moving close to the source, then we want the new frequency to be larger than the old frequency. So if we're trying to make this value larger, should you add these two things or subtract? Remember that if you have a large numerator, we're going to have a larger quotient, or a larger f prime. So if the detector is moving close to the source, then we add, okay? Because we want to make this value as big as possible. Actually, not as big as possible, but we want it to be bigger than this value. So now to the source. If the source is moving towards the detector, then we want to increase this value. If you want to increase this value, then you have to subtract. We have to add a negative sign. Because the smaller the denominator gets, the larger the f prime gets. And this is the way basically to understand how to use this equation. And we have four possibilities. If you have a detector that is moving away from the source, then we're going to use the negative sign. Why? Because we want to make this smaller than this. And remember that a small numerator is going to give a smaller quotient. And in this same scenario, the detector, or the source, is moving away from the detector. So we want to add a plus sign between these two, because the larger this gets, the smaller this gets. So away will result in a smaller frequency. If the direction of movement is away from each other, away from the other actually, if either the detector or the source is moving away from the other, then we're going to have a smaller frequency. And if it's closer, then we're going to have a bigger frequency. Okay, so we want to apply this rule over here in situation 3. So if the detector is moving away from the source, then we want to subtract here, because we want to make the numerator as small or smaller than this value. And in the same equation, the source is moving towards the detector, so we're going to use the negative sign here, because we want to make the denominator as smaller than this value. In fact, we want to make the denominator small because we want to increase this value. So the smaller the denominator gets, the bigger the f prime gets. And for the fourth scenario here, we're going to have the detector moving close to the source, so we're going to have a positive sign here. And the source is moving away from the detector, so we're going to have a positive sign in the denominator as well. Okay, so two rules to remember. This rule right here, and the idea that if we divide two things, then the numerator, if it gets bigger, then this here will be big. But the denominator is like the opposite. If this gets too big, then this gets too small. And that's it. If you understand this and understand this, you'll be able to use this equation successfully. Alright, so a fun way to conclude this chapter is by looking at something called supersonic speed and shock waves. So if you have an object, say, that is moving at 343 meters per second, which is the speed of sound, and the medium here is air, okay? So if the object or the source, this is a source of waves, say a speaker or something like that. So it's moving at the speed of sound, so the sound waves are going to be looking like that. So the object here, like near the object, there will be no frequency, and there will be a very large frequency like in the other end. Now imagine that an airplane, for example, that we have a stereo in an airplane, and this airplane go beyond the speed of sound, say 500 meters per second. Then this object that is moving at this speed is said to be having supersonic speed. So supersonic speed is, or means that we're moving in a speed that is higher than the speed of sound. Okay, so there is a relationship between sound wave in the medium, which is this value, if the medium is air, and the velocity of the source. So if you divide the velocity of the sound in the medium by the velocity of the source, then that is going to be giving you the sine of this angle. So first, if you move beyond the speed of sound, then your sound waves are going to be looking something like this, and you're far away from the waves because you're moving faster than them. Okay, so that being said, like if an airplane is moving at the speed of sound, then suddenly increases its speed to a speed that is higher than the speed of sound, then something that is called shock waves are gonna occur. So a shock waves is like an explosion or something like that. Like it has something to do with entropy and thermodynamics, and there's a lot that goes into that, and we didn't study this in this course. But so when shock waves occur, like a sudden drop in pressure occurred, like this is time and this is pressure. Actually, it's not going to look something like this. If pressure was like that, at the moment of shock wave, it will drop like this. So, and because of this drop in pressure, the air molecules, say we have, we're in an airplane and there's a lot of, clouds. So we have water molecules. These water molecules are going to be condensed because of the drop in the pressure. And the gas water is going to be turned to liquid water. And we're going to see something like fog, a lot of fog with the airplane. So if this is an airplane, the shock wave are going to be looking something like this. So this here will be condensed water. So there's a picture in the book, actually, at page 447. Take a look, it's a pretty beautiful picture, and it's a picture of a plane that is moving. It's actually a picture at the moment the plane exceeded the speed of light, sound, and at that moment we had a shock wave. Yeah, and finally there is something called Mach's number. So Mach's number is the velocity of the source, say the airplane, divided by the velocity of the sound. So if we have an airplane that is moving 3 times the speed of sound, if you divide that by the velocity of sound, these are going to cancel, and we're going to have a Mach number of 3. So if somebody tells you that an object is moving at Mach's number 3, then it means that we're moving at 3 times the speed of sound. And that's it. That's everything in this chapter, and I hope you enjoyed this video. Do let me know your comments and constructive suggestions and whatnot. And like and subscribe to the channel. Thank you.